Participant, he's actually a Punahou School student entering his senior year. So he was a junior mentor for the entire program and specifically for this group. And so on my right here I have Alexis Bermudez, then Regina Miner, Malia Swartz, and Connor Lee.
Where's Waldo? Discovering a transiting extrasolar planet. The purpose of this project was to determine which star has an extrasolar planet orbiting around it by measuring the brightness of certain stars. Before we move on, I wanted to share with you guys some background information just in case you didn't know much about this topic. Extrasolar planets are actually planets outside the solar system. Currently, there are 552 extrasolar planets that have been identified. Hot Jupiters are planets that are greater than the size of Jupiter that are very close to their star, which causes them to be hot. The main way of detecting these planets is called radial velocity. We actually didn't use this method. We used the transiting method. By searching these exoplanets, we can find the possibility of extraterrestrial life.
This telescope right here, this satellite right here is a coral convection rotation planetary transits. That was specifically designed to find extrasolar planets. It has a large field of view but relatively low resolution. Consequently, it can only determine the general area of the star with an exoplanet, but not the star itself. Our job is to find the exoplanet ourselves.
So this is an animation of a transit. When the planet goes in front of the star, as you can see, the light curve decreases because the amount of light that we observe decreases. And then when the planet goes directly in front of the star, the light curve decreases even more because there's even less light that we can observe, and then vice versa. So our hypothesis was, if there's an occurring transit, then a dip in the light curve would be expected because the planet would block the parent star's light.
Some materials that we used for this project was Myra, which is a photometry program, and the Fox telescope to collect all of our images, as well as a computer so that we could complete all of our procedures, internet to do some beforehand background information, and Microsoft Excel to organize our data and create all our graphs. So to start off our project, we collected images from the Fox telescope, and our data consisted of 172 images that looked like this. So we start off by correlating the finder chart. So we had to find this small picture in this larger image, which is the area of the sky we're looking for. And it was very time consuming and very difficult. Hence the name of our project, Where's Waldo? So after that, we focused on the finder chart itself by numbering the brightest stars. So we came up with 6 target stars and 1 reference star. And we registered the images on Myra so that they were all in line. And then finally did the photometry, which is measuring the brightness of an object over time. So these were our 6 target stars. So 1, 2, 4, 5, 6, and 7. And 3 was a reference star. And we created a flux ratio with the data that we got from Myra. And a flux ratio is basically the net count of the target star divided by the net count of the reference star, so that you can deplete the atmosphere's effect or any outside light sources that will interfere with the data. And we created a graph that includes the flux ratio as the y-axis and reduced JD, which is Julian date. And we repeated this for every star so that we could figure out which star the transit occurred in.
these are our results. So these are results on 6 different stars that were possible candidates of being the parent star that we were looking for. On the x-axis is the Julian date. It's reduced. And from this point to this point is approximately 230 minutes. We were unable to create a full light curve because we didn't have the data, so we were looking for the ending part of the transit. As you can see, this is the ending part of the transit. This is target number 5, comparing to target number 1 and target 7, and target 2, 4, and 6. There are fairly straight lines compared to target 5. In conclusion, our hypothesis was supported because we found a light curve, which suggests that there is a planet transiting around the star. This is significant because we were actually the first group to confirm this extrasolar planet's existence. In the future, we plan on continuing our projects and entering science fair, work with people from Falks, and stay in touch with our fellow astronomers.
Before we conclude our presentation, we'd like to give a special thanks to our mentors, Dr. J.D. Armstrong and Travis Lay, Ms. Marianne Karuoka, the director of High Star, for giving us these great opportunities, as well as the people from Falks for helping us.
Okay, so to see if you guys were paying attention, how many of you can guess how many Waldos there were?
14.
Oh, the tiny ones? The tiny ones. There were 14 tiny ones. And then the big Waldo there, and then the big one at the top.
Oh, I didn't know that.
Well, sorry. Thank you for paying attention.